Swayam Prabha. Digital India. Educated India.
So we have looked at one kind of a processor known as a hardwired processor. So in this hardwired processor, the main brain of the processor is the control unit. The control unit, as we have just seen, generates all the control signals, and these control signals control the movement of data inside the processor, right? So for different kinds of instructions, different control signals are generated. So this kind of a processor with a hardwired control unit is fairly common. In fact, that's the standard. But there is another kind of processor as well that gives us a lot more flexibility. In certain situations, it is used also in modern processors such as the Intel line of processors. There are some instructions which run, so essentially the processor itself contains a hardwired part and what we call a microprogrammed part, where some very complex instructions are implemented using the latter, the microprogrammed part. So let's take a look at a microprogrammed processor in slightly more detail. So what's the idea of microprogramming? So in this case, we expose the internal elements of a processor pretty much to software, right? So to the assembly programmers, we expose the internal details of the processor which were otherwise hidden. So this allows us to pretty much code an instruction, right? So consider an add instruction. An add instruction is doing many things. So what we can do is that we can add a new instruction or modify an add instruction to, for example, instead of add 2 numbers, add 3 numbers, right? So we can change the behavior of instructions. We can do many more things. And we can also add very, very complicated instructions which are like add, register the contents of R1 and R2 and multiply them by 37. So we can, introduce an instruction of this kind, right? 37 times R1 plus R2. So, we can definitely introduce instructions of this kind. And this, we are searching for such kind of a processor which can give us this flexibility of doing many things, implementing. So let me walk backwards, implementing complex instructions, fixing bugs in the implementations of current instructions, and also changing the behavior of instructions. As I said, instead of an add instruction, we can replace it with this if there is a requirement by applications. So all of this is great. This comes at a price, and the price is speed, of course. So processors with hardwired control units are much faster, and processors with microprogramming are relatively slower. So the price is speed and efficiency. So we need to create a microprogrammed data path. So microprogramming is different from conventional programming because in this case we are writing the code for each instruction. So that's why it's microprogramming. So what we do is that we expose all the state elements inside a processor to system software. So, so this is also known as firmware, where we can write dedicated routines in firmware, which basically means the part of the system software that very intricately controls the behavior of hardware. This can be done for implementing each instruction. So the way that we look at, we have conventional software, we have conventional hardware, and we can have a small thin layer in the middle called firmware. So firmware is still software, but we still distinguish it from it because unlike traditional software, the firmware is loaded or stored in a specific location in hardware, and it is used to very intricately control all that the hardware does. So it has far more visibility into hardware as compared to traditional software. So that's the reason we refer to this layer as firmware, and is a very common term in the systems community. So you can have firmware for all kinds of systems. You can have firmware for disks, you can have firmware for network cards, for routers, everything, right? It's possible to have a firmware layer, where firmware is again software, but software meant for a different purpose. So let me talk about the basic idea of microprogramming. So in this case, we take one simple RISC instruction, right? Like add, subtract, multiply, and we break it into several small micro instructions. We execute each micro instruction pretty much one every cycle. And so pretty much what we do is, for an add instruction, we replace it with a micro program which can have many micro instructions, right? So what we do is that we start from the top and keep on executing till the bottom, and so basically this is a small program by itself, where instead of one high level RISC instruction, we execute several micro instructions. Once this micro program is done, so it's typically represented something like this micro program. Once this is done, it means that we have completed finishing the execution of this instruction. So we require a microprogram counter and a micro instruction memory, very similar to the PC that we had, and the instruction cache, the instruction memory. Sorry, I shouldn't be using the word cache here because we have not introduced it, but the instruction memory, right, that we have been using. Alright, so let's now, this also has different units, so let's take a look at the fetch unit. So in the fetch unit, we still have the PC register here. So the PC register is used to access the instruction memory and load the contents of a regular simple RISC instruction. The contents of the instruction are saved in the instruction register IR. So mind you, this is a micro register, and this micro register, which we are calling IR, instruction register, contains the contents of the so basically contains the contents of the instruction, where its address is given in the PC. So this is the address of the high level simple RISC instruction. We use this to access instruction memory, and the contents get transferred to the IR register. Let's now take a look at the decode unit. So in the decode unit, the input pretty much comes from the IR register, and so then what a little bit of circuitry does, which is pretty much hidden, is that we extract all the fields from the IR register. So for some instructions, some of the fields might not make sense, they might contain junk, but nevertheless we extract all the fields. For example, we extract the I bit, the immediate bit. We extract the RD field, which in normal cases stores the ID of the destination register. We extract the first source register, the second source register. We also have an immediate unit that extracts the 32-bit extended immediate after taking modifiers into account. So it extracts the immediate, right? So basically the 18-bit immediate is extracted to a 32-bit immediate. So recall that an immediate in simple RISC is actually 16 bits plus 2, where the 2 bits specify the modifier. So the 32 bits are available in the IMX register. In addition, what we do is that we take the offset part from the instruction. So of course at this point we don't know what is the type of the instruction, but we prepare for all kinds of instructions and we pre-compute all of these terms, right, the immediate and also the branch target. But of course it's not necessary that every instruction is a branch. So if an instruction is not a branch, this micro register will contain junk. But nevertheless, in the interest of time and performance, it's a good idea to compute things in advance just in case they are required. So to compute the branch target, what do? We extract the offset part from the instruction register, add it to the current PC, and we get the branch target. So we also compute this. All of these registers are connected on a shared bus. What is a shared bus? So a shared bus is basically a set of copper wires to which all of these registers are connected. But it is not the case that all of them are feeding their data to these copper wires, right? So then it will not work. So by default, these links between the register and the bus are actually turned off, or they are open circuits. But it is possible for us, as we shall see in the next few slides, to occasionally read these registers. So to read these registers, or rather micro registers, what we need to do is we need to send a command, for example, to read IMEX, and then this connection from IMEX to the bus will get enabled, and what we'll see on the bus is the value of IMEX which others can read. After reading, again we'll send one more command, or automatically this link will get cut off and the bus will not contain the value of IMEX. So what again is a shared bus? It is a set of shared copper wires. Alright. So now let's take a look at the next stage, right? The execution stage, the EX stage. So this contains the register file. So what we shall do, we augment this part of the processor with actually 3 more micro registers. So the micro registers are as follows. So one of them is reg source. So reg source is the register that we want to access, either for read or write, it doesn't matter. But reg source contains a 4-bit value, mainly because we have 16 registers, and this is the ID of the register that we want to access. Then we have reg data, which means that if we want to write to a register, then the value of reg data will come from the shared bus. It will be saved in the reg data micro register, and from there it will go to the register file. The args, or the arguments, basically specify whether we want to do a read, read a register, or write to an actual register. So mind you, the register file here is exactly the same as the previous processor, right? So let's maybe adopt this convention that whenever I introduce a new structure for the microprogrammed processor, I'll separately specify, use the word micro register as far as possible. Otherwise, almost everything remains the same. And alright, so what is reg data again? So when I'm writing to a register, reg data contains the value that needs to be written. Assume that I want to read a register, then the value of reg data is irrelevant, so it will not be read. However, the value of the arguments will be equal to R, which means I want to read a register. The ID of the register will be there in reg source, and the contents that are read from the register file will go and will get stored in the reg val micro register. Subsequently, if some other stage, if some other part of the processor wants to know what exactly was read from the register file, then the reg val micro register can supply the value on the shared bus. Alright, so we have reg source, which contains the ID of the register, reg data, which contains something if something has to be written, and reg val, which is the value of the register which was just read. Alright, let's take a look at the ALU. Okay, one small correction here. In this slide, I had incorrectly mentioned that this is in the execution stage. That is not correct. This is still a part of the operand fetch, or the OF stage. So this is one correction that I would like to make. Alright, so now we enter the proper EX stage. And the EX stage, the main elephant in the room for the EX stage, the ALU. So controlling the ALU is easy. So what we have done previously is that we have kept, so the pink boxes here are artifacts of our earlier hardwired processor design, and these are all the new elements. Alright, so basically this light brown color, these are all the new elements that we add. So let's take a look at them. So let's assume we want to perform an ALU operation. If you want to perform an ALU operation, then we'll have 2 operands, right? Most of the time we'll have 2 operands, like add, multiply, subtract. Sometimes we'll have one, we'll take a look into that, but most of the time we'll have two operands. So we'll add one 32-bit micro register called A, which stores the first operand. We'll have one more 32-bit micro register called B, which will store the second operand, right? That we will read from the shared bus. So the second operand will be stored in micro register B. Args, which is incorrectly specified here, will contain the nature of the operation that the ALU needs to perform. So I should rather write nature of the ALU operation. Add, subtract, multiply, what kind. So args will contain the nature, what exactly you want the ALU to do. So that will be there in args, and all of them will be read from the shared bus. So it is not that all of these units are active all the time, but we'll have a way of activating only a certain subset of these units depending upon what needs to be computed. So let's assume that the ALU is active, so it will read the contents of args directly from the bus A and B. After that, the result of the ALU, after the computation is done, towards the end of the cycle will be stored in another micro register called ALU result. And for each of these micro registers, they will contain their value till they are overwritten. So ALU result can further supply this ALU result micro register can supply the value to others units on demand, of course, via the shared bus. So everybody operates via the shared bus. Similarly, we'll have our flags register that we have discussed in our previous lecture. So which stores the flag of a compare, and we'll also expose the flags. So we'll have two small sub micro registers, flags.e and flags.gt, E for equality and GT for greater than. So these two sub micro registers will also be able to export their values on the shared bus to whoever who requires it, right? So these are all the micro registers, that we add in the ALU stage, A and B. For the inputs, ALU result contains the output, flags.e and flags.gt contain the results of the flags. So recall that it's only the CMP instruction that changes them. Otherwise, the flags values reflect the state of the flags that was set by the last CMP compare instruction. Alright, now let's go to the MA stage, the memory unit. The memory unit does something very similar. We add, following the same line of thought, we add micro registers to the data memory. So we add a memory data register, MDR. Similarly, we have a memory address register. The value of the args say whether the operation is a load or a store, right? Which operation it exactly is. So whenever we are doing a store operation, we'll send the memory address via the memory address micro register, and the data that needs to be stored will come via the shared bus to the memory data register. Subsequently, and also the type of the operation, which will be a store. This will go to the data memory where the store will be affected. If the operation is a load, then of course the args here will contain the fact that this is a load operation, and so the MDR will not have any value, but the load will have an address. So the address will be stored in the MAR or memory address register, and the result of the load will be stored in another micro register called LD result, load result. This is similar to ALU result, exactly similar in spirit. So this will contain the result of the load, which can be given to others on the shared bus. Alright, so what we have done is we have taken again our old unit, which is the data memory in pink, And we have added three new micro registers: MAR for the address, MDR for the store data, and load result for the data that we read from data memory. So we add these three micro registers. Alright, so what does our microprogram data path look like now? This is what it looks like. So what I've done is I've taken all the small diagrams that we have been introducing over the last few slides, and I've collated them into one large diagram. So let me start from one side. So given the PC or the program counter, so this is connected to the shared bus, of course. And so this was not, maybe it was not mentioned in that slide, but it needs to be connected to the shared bus both for read and write. It accesses the instruction memory. The contents of the instruction memory go to the IR instruction register, which contains the contents of the instruction. We have a little bit of circuitry that breaks the instruction into its constituent fields, namely the immediate bit, RD, RS1 and RS2 fields, the extended immediate, the 32-bit immediate that we get from the 18 bits embedded in the instruction. We also calculate the offset. There will be an offset, some bits in the instruction specify an offset, so we add it to the PC to get the branch target. Simultaneously, the instruction, particularly the opcode of the instruction, goes to the microcontrol unit, which decides, for one given instruction, for every separate instruction, there is a separate microprogram, so it decides which microprogram needs to be run. And based on that, it runs a separate microprogram for each instruction. So what again is the advantage? Well, the advantage is we have complete flexibility, as we shall just see. So we can add new instructions, we can change the behavior of existing instructions, and all of this can be done at the level of firmware, right, which is very, very specialized software. So for example, a processor is sold and it is a part of a system. After that, we can change the way its add instruction operates. So that's pretty cool in a lot of cases. So to do that, what we need is that we need to consider some of our main functional units that were there in our previous processor. For example, the register file, ALU and data memory. For each of these, we add micro registers between the unit and the shared bus. So the micro register buffer the inputs and also store the outputs. And the outputs will remain in that state till the unit is accessed once again and the inputs or the outputs are overwritten. And to control the units, we have some bits that come from the shared bus, namely the arguments bits, to, for example, tell the register file to read or write, or to tell the ALU what kind of operation it needs to do, or to tell the data memory whether it's a load or a store. Once the operation is complete, the results will all be there in these result micro registers: load result, ALU result, and regval, which can then be used by other units if required. So we shall see when we shall write microprograms, we'll see how all of this works. And the crux of the entire processor is a microcontrol unit, which runs the microprogram for each high-level simple RISC instruction, and the shared bus, which conceptually is just a set of copper wires. Now that we have seen the microprogrammed processor, let us look at microassembly language. So before we begin, let's look at all the registers that we have introduced. So we have taken the PC register from our previous implementation of a processor, and this is the typical program counter, so no changes in that. We have introduced the IR register to contain the contents of the instruction. The I instruction is a single bit, the I micro register, which is single bit, the immediate bit. RD, RS1 and RS2, which contain the destination register ID of the first and second sources. The 32-bit extended immediate stored in the IMEX micro register, the branch target in the branch target micro register, reg source, reg data, and regval which encapsulate the register file. Similarly, A, B, flags.t, flags.gt, and ALU result, which encapsulate the ALU. And finally, the MAR, MDR, and load result micro registers, which encapsulate the data memory. Alright, so let's introduce some basic instructions. We don't want to introduce many, but let's at least introduce a few, right? As many as are required. So the basic instructions, or rather basic micro instructions are, so let's make a convention that we'll start all micro instructions with the letter M. So let's look at M load IR. So M load IR loads the instruction register IR with the contents of the instruction. So whatever are the contents of the instruction, right, they come from the instruction memory and get stored in the instruction register IR. Fine. So this is M load IR. Next is M decode. This is a one cycle instruction where all the decode registers get populated. So we read the contents of the instruction from IR, and all the decode registers, which are essentially the immediate bit I, RD, R1. So recall that we are interchangeably using the term micro register and register. So please infer them from the context. So our decode micro registers are RS1, IRD, RS1, RS2, MX, and branch target. Sorry. All right, so these are our decode registers, micro registers. So what we do is at the M decode instruction, we wait for one cycle, and in the one cycle, we expect that the circuitry that takes the contents of the instructions from IR would have populated each of these registers here, right? Subsequently, once we have decoded, we call the M switch micro instruction, which loads the set of micro instructions corresponding to a given program instruction. A simple RISC instruction. For example, if let's say the program instruction is add, we will know that it's an add in the decode stage. So this will go to the microcontroller, and this will load the set of micro instructions into some internal storage, such that for an add instruction, we can execute all the micro instructions that correspond to it. So this will happen with the M switch instruction. Now let's also take a look at two more instructions which are very basic. So all the instructions in the microprogram pipeline are actually extremely basic. So we have taken a look at mload IR, which essentially loads the contents from the instruction cache to IR register, mdecode, which simply does a decode, and mswitch, which for a given simple RISC instruction loads its corresponding microprogram. So mmove and mmove are slightly different. So in mmove, given two registers R1 and R2, it simply takes the contents of R2 and puts it in R1. We have another variant of mmove where it additionally takes a few bits called the arguments. So what it does is that it puts R2 in R1, that it does, and it also sends the value of args on the bus. Alright, so basically it does these two. If an additional set of arguments are present, then the value of the args field is sent on the bus, on the shared bus, that is. So this is what mmove does. It comes in two formats, one with arguments, one without arguments. And we have mmove I. So mmove I is mmove immediate, where given an immediate, the immediate is moved into the register R1. Right, the first register, whatever it is. But mmove I pretty much moves the contents of the immediate into the register. We have a few more. So we introduced three very basic instructions which are micro instructions which are required for every instruction, namely mload IR, mdecode, and mswitch. We then introduce two generic move instructions, mmove and mmove. So one to move a register, one to move an immediate. Now we need a little bit of add and branch micro instructions. So the add micro instruction that we shall introduce is madd. So it takes the first argument as a register, the second argument is an immediate, and the third argument is basically a set of bits called the args field. So what it does is that it sets R1 similar to x86 where the one destination and source they are common. So we have it in a similar way where R1 is set to the old value of R1 plus the immediate. So R1 is equal to R1 plus the immediate, and we send the value of args on the bus. The arguments we send them on the bus. Similarly, we have MBEQ. MBEQ it's a micro branch if there is an equality. So the equality is like this: we specify a register, specify an immediate, and a label, a micro label rather. So if R1 is equal to immediate, which means if R1 is the same as the contents of R1 is the same as the contents of IM, we set the micro PC in the micro program to the address of this label. So this is an artifact of traditional assembly. So it works in exactly the same way, but it's just that we send a register and an immediate, we compare them. If the comparison is successful, we do a branch. We also have an unconditional branch MB, which just takes a label when we set the micro PC to the address of the label, unconditionally. So we introduced three new micro instructions on this slide. madd for a micro instruction addition, mbq which is a conditional micro branch, and mb which is an unconditional micro branch. Alright, so let's summarize the 8 instructions that we introduced. The 8 instructions that we introduced are like this. That we introduced the mload IR micro instruction, which takes the contents of the instruction memory addressed by the PC and puts them in IR. mdecode populates all the decode registers. mswitch will jump to the relevant microprogram counter corresponding to the opcode of the simple RISC instruction. Then we define 3 instructions which actually use the arguments, and they can have different variants with or without arguments. But let's assume that even if arguments are not there, it's still part of the same generic variant where the arguments are not there, right? So, for example, in the mmove micro instruction, which takes a register 1 and a register 2, we set register 1, the contents of register 1 to the contents of register 2. And these are all micro registers. And we send the value of args, right? So we send the value of args on the bus. In specific, we send it to the unit that owns reg1. For example, if we send it to ALU result, it'll essentially go to the ALU. So since it's sent on the bus, theoretically everybody can read, but the unit that owns a certain register is the one which is supposed to read and process it. Similarly, we have the mmove instruction, which moves an immediate to a register. And so here also args is optional, but it works in exactly the same manner, where args is sent on the bus and the unit that owns reg1 ends up processing it. We have madd, which does the same thing. It sets reg1 as reg1 plus im. Args is again optional, but it does the same thing. We have two kinds of branches, MBEQ and MB. MBEQ is conditional upon equality, that if a given register is equal to an immediate, then we set the micro PC to the address of the label. I would not put an address here, I would rather put a label, so that's a mistake. So here, whatever is the address corresponding to the label in the micro program, right? That will be set to the value of the micro PC. And MB is an unconditional branch. So that's an unconditional branch. So in this case, we will jump to the label in any case. So the micro PC is set to the address of the label. So these are the only 8 instructions that we introduce, and we'll use these 8 instructions to do all our work. So every every instruction in its microprogram will always have some instructions in common at the beginning. That is called the preamble, right, of every microprogram, which is common. So this preamble, we have made it start at the dot begin label. So the assembly format is also the same as simple RISC, which we introduced in chapter 3. So here we start with mload IR. We have to, because we need to read the contents of the current PC. Then we decode. So this is again common. Then we call the madd instruction to increment the PC by 4 bytes to go to the next simple RISC instruction. So basically we have PC equal to PC plus 4 over here, and which means next time that we read the program counter, it will be the next instruction, next simple RISC instruction. And then we start executing the loaded microprogram. Then we actually load the microprogram, and we call mswitch. So mswitch does many things. What it does is it switches to the first micro instruction in the microcode sequence of the program instruction, of the simple RISC instruction. So it does two things. One thing is, given the simple RISC instruction, it first figures out which microprogram it's supposed to execute. Then it also moves the micro PC to the first instruction in that microprogram. And for example, add will have a separate microprogram. Subtract will have a separate microprogram. So whenever we encounter subtract and we have decoded it, when we call mswitch, it will move the micro PC to the first micro instruction in the microprogram, in the part of the microprogram that is specific to the subtract simple RISC instruction. So the preamble remains common. So all instructions will have to execute the preamble first, which are these 4 micro instructions. These are absolutely common. After this, the micro instructions will be different. So let's now look at the microcode of different high-level instructions. High-level meaning simple RISC instructions. So let's first consider 3 address format ALU instructions, something of the form add R1, R2 and R3, right? Something of this form, where we actually do R1 is equal to R2 plus R3. So what we do is that we first read all the values, we transfer them to the ALU, and then we perform the ALU operation. So the first step is we need to read the sources of the ALU operation, which in this case, in our running example is an add operation, but it can be any 3 address format ALU instruction. Then we do the ALU operation and we write the result back. So there are many steps here. Let's take a look. So the first step, which is the first 2 lines, is to transfer the first operand to the ALU. So what we do is that we issue an mmove instruction. The mmove instruction accesses the RS1 register, the first source, and then it transfers its content to the reg source, right? So recall that the register file, the reg source instruction encapsulates it, and it contains the ID of the register that needs to be accessed. So we take the contents of RS1 and put it in reg source, and further what we do is that we send the arguments read on the bus. So which means that 2 things will happen. What will happen is that the contents of RS1 will go to the register file. They'll be saved in reg source. Simultaneously, the read operation will be initiated in the register file, and the register file will take the values from the reg source field. So think of it this way: on the shared bus, the register file is connected. Two things are coming together. One is that a read operation is coming from the bus. Also, what is coming is that the contents of RS1, the contents of RS1 will actually be the register R2. So the register R2, that ID is coming. It is going into the reg source micro register, and simultaneously it is going into the register file, right? And so basically we are doing a register file read access also simultaneously. So we are doing two things. Maybe this diagram is small, so let me draw it once again. So it's very important to appreciate that we are actually doing two things over here. So let me draw the shared bus once again. So what we are doing is that, and also here we have the RS1 register. So what we are doing is that we are executing an assembly instruction which in hardware is telling the RS1 micro register to send its value on the shared bus. And once something is sent on the shared bus, everybody will be able to pick it up. We are also telling that let's send the read command on the shared bus as a part of the arguments. So then the register file will see that the read command is meant for itself, so it will activate itself, and it will see that a read is being sent. Along with that, the contents of RS1 are being sent. So it will do two things. We are also asking the register file to move the contents of RS1 to reg source. So it will do that. The contents of RS1 will be moved to reg source. In addition, since we have sent the read command, the register file will take the contents of RS1, and along with writing it to reg source, in parallel it will start performing the register file read access. So it will do two things: write to reg source, and since arguments have been set, it will use the contents of RS1, right, which it will treat as the source contents, which it will treat as the ID of the source register to access the register file. Then it will store the final result, the computed result, in the micro register regval by the end of the cycle. Subsequently, what we will do is that we will move this to register A, which is a part of the ALU's system, right? ALU has two input registers A and B. So whatever is there in regval in the next cycle, we will transfer the contents of regval to register A again via the shared bus. But since there are no arguments, nothing needs to be done. Alright, so let me erase the ink on this slide and let me move to the next part. So here what we do is we check the value of the immediate register. So we compare the contents of register I with the value 1. If I is equal to 1, it means that the immediate is set to true. So we will jump to .im, which is over here. Here what we do is that we transfer the contents of imx, which is the extended immediate, to the register B. So recall that the ALU is also connected to the shared bus. Via the registers A and B. Then the args are also coming in, and this is the ALU. And we also we can optionally send this data here if it's a simultaneous thing. which is exactly what we are doing here. So we are sending MX on the bus. MX is being written to micro register B. In addition, we are sending the ALU op, ALU op argument, which is basically what operation we want to do on the ALU, which can be add, subtract, multiply, all other, compare all other ALU operations. These ALU operations are being sent to the ALU. So when the ALU sees that a command via the args field is being sent to it, it activates itself and it takes a look at what other data is being sent. So the value of MX is being sent and this is being sent to register B. So along with writing it to macro register B, it will also go to the ALU. And since A was already populated over here, both the operands are there in A and B, so the ALU will start doing the ALU operation. Let's take a look at the other branch of the if statement. If uh, the immediate field was 0, which means the second source operand is a register, right? If the second operand is a register, then we read the contents of RS2, which is exactly this statement repeated once again, that we read the contents of RS2, transfer them to reg source. Reg source is a micro register that encapsulates the register file. Simultaneously, we send the read argument on the shared bus. So along with writing the value of RS2 to reg source, it will also read the register file with whatever value is being sent. The output will be written to the reg val micro register. So again, a statement similar to this will be executed here. So since the value of A is already there and it has been set in advance, and now some ALU operation, add, subtract, multiply, whatever is coming via the bus, and we are writing the some value is being written to macro register B, we can write it to macro register B and also in parallel send it to the ALU, and the ALU will then process the contents of A and B and the ALU operation and write its result. So after this we move to the next micro instruction, and so we don't want to enter this part, so we'll directly make a jump, an unconditional jump to the RW label, where the RW label is here, so we'll execute this instruction. What we will now do is that we'll start the procedure to write the ALU result to the register file. So let me do a partial erase. So in the register file, we have the reg source micro register, which contains the source, which contains the ID of the register that needs to be accessed, and we have the reg data micro register, which contains the data that needs to be written. And then again, of course, we have the shared bus. So what we do is that we move the contents of the RD register, which contains the ID of the destination register, to reg source in the first cycle. So we don't access the register file because there are no arguments, so there is no command, but we populate the reg source micro register with RD, right, the ID of the destination register. Since the result of the ALU operation is there in the ALU result micro register, we transfer this to reg data via the shared bus, of course. So ALU result, which has the result of the last ALU operation, its data is transferred to reg data because this is what needs to be written. And since the ID is already there, we can simultaneously send a write signal via the args argument to write to the register file. So in this manner, what we do is that we first read data from the register file in these statements, or we read the immediate, with this statement and this statement, or we read the immediate over here. We perform the ALU operation and then we write the result of the ALU operation back to the register file. Once we are done, we make an unconditional jump to the begin label And recall that the begin label is the beginning of the preamble, where there are first a fixed set of instructions that we have to execute, and then we move to the particular microprogram, of each and every simple risk instruction. So now, the important point, of course, see, a large part of this is very, very straightforward of just moving things around. But the important point is an instruction of this type. So recall that two things are being done here. First, we are setting the contents of reg source to the contents of rs2. That is one thing. In parallel, I remind you, in parallel, simultaneously, concurrently, we are also accessing the register file. Why are we doing that? Because the command is being sent via the bus, via the args field of the bus, to the register file to either read or write. In this case, it is read. Doesn't matter, it can be read or write. Since a command is being sent, we'll activate the register file. And since it's a read operation, we will read the data from the reg source micro register. So we allow a concurrent writing of this micro register and also reading of its value. So we'll need to have a very small forwarding circuit. But that's a very simple detail. I'm ignoring that. But pretty much the reg source micro register needs to be accessed. We need to get its current contents. If its current contents are being written to, are being modified, that's okay. If whatever we are writing, we can sort of bypass the value. That's all right. And then we can start the access. So in this case, we save one cycle. So this is an interesting, neat, elegant, efficient optimization to make. We do the same thing for an ALU operation as well, where we also write the value of regval to microregister B and also simultaneously initiate an ALU operation. So this can be done, and with a small forwarding path, this can be done. So this is per se not a very technically challenging operation. Alright, so now that we have seen a difficult set of instructions, namely 3-address format ALU instructions, let's take a look at something similar yet significantly simpler, namely the move instruction. So this is easy. We first check the value. So since I have also discussed the format of most of the instructions, I'll go slightly faster. So we check the value of the immediate register. How do we check? We compare I with 1. So we read the value of the I micro register, which has been populated in the M decode step. We compare it with 1. If the comparison is successful, which means I contains 1, we directly jump to .im. So what we do is that the contents of imx, right, the extended immediate, are written to reg data. So reg data, recall, is the register which contains the data that needs to be written to the register file. Otherwise, the second operand is a register, right, because the immediate is 0. So what we do is that we read the contents of rs2 and transfer it to reg source, and simultaneously we also send the read command on the bus. So it initiates a register file read, and the results of the read are stored in the regval micro register, right? So the register file, this is the register file. We have reg source, which is the ID of what needs to be read, and we have reg data, which is the contents of what need to be written, and then we have the output of the register file as regval, right? So what we do is that we send the contents of rs2, so we read one of the registers, right, the second register, second operand. Then what we do is, once we read it, we again need to use it to write it to the destination. So we transfer the contents of regval to reg data by this move instruction. Then we do an unconditional jump to RW, which brings us over here. So since the correct ID is loaded in reg source, no, not yet, I'm sorry. So then what we need to do is we need to load the ID of the destination register in the reg source micro register. So what we do is we read the micro register RD, which contains exactly this information, and this is transferred to reg source. And since in advance we have already written the right data that needs to be written via this statement over here and this statement over here, either the immediate or the contents of a register have been written to reg data, we can in parallel initiate the register file write by sending the write command, which is exactly what has been done. And thus what we have done is that if let's say we want to set R1 to R2, we essentially read the contents of R2 and transfer it to the destination register R1, which we have just done. We have either read a register or an immediate, and we have written it to the destination register. Once we are done, we jump to the beginning of the preamble by the micro instruction mb.begin. Now let's take a look at the not instruction. A little bit of a problem here. This should be not. So here we do exactly the same thing, but we need to do a little bit more. So this is essentially a to address format instruction. So we do a little bit more. But recall that, try to understand that all the programs are written more or less in a similar fashion, with a little bit of difference here and there. So what we do is we check the value of the immediate register. So we again compare it with 1. If the second operand is a register, we do something, otherwise we do something else. So we have always been looking at the first case, the case when the operand is an immediate. So let's take a look at it first. If it's an immediate, what we do is that we access the IMEX micro register which contains the immediate. We move it to the ALU micro register B. Why? Because recall that the ALU is encapsulated with two micro registers A and B, and we have always, even back in chapter 3, we have used B as the source of data for the NOT instruction. So we'll do the same over here. We'll populate the B micro register. It will send its contents to the ALU. And since this is a single operand ALU instruction, we can in parallel initiate the ALU operation as well by sending the command NOT, right, the NOT ALU instruction on the bus. So the ALU in one cycle will be ready with its result. However, if the second operand is not a register, is not an immediate, it is a register, we need to do something else, which is that we need to access the RS2 micro register, which contains the ID of the source operand. We need to this is a register ID, so this needs to be transferred to reg source as we have been doing. And in parallel, we can issue a register file read. So in one cycle, the data will be ready in the regval register. So this we need to do exactly the same as we did here in this line. That regval will send it to the ALU register B, and in parallel also issue an ALU operation to compute the NOT of the value. Once done, once we are ready with the ALU result, we do an unconditional jump to RW. So irrespective of how we get here, so let me, slide is getting cluttered up, so a little bit of cleaning is due. So irrespective of how we get here, what we know at this point is that the ALU has computed its value, and the value is present as of now in the ALU result micro register. And the value can come from two sources. It can either come from IMEX, which contains the immediate, or it can come from the register file where the ID of the source register is in RS2. In both of these cases, we have transferred the data to the ALU with uh, the command specifying that do compute the NOT operation. So once done, what is left? We need to write the result to the register file. So we transfer the contents of ALU result to the micro register that contains what exactly needs to be written to the register file, which is reg data. So the reg data micro reg is populated here, and we read the RD micro register that contains the ID of the destination register. This is sent to reg source. So we have a register file, and the register file has, this is an F, okay? It's an F. So it has reg source for the ID of the register and reg data for what is it that needs to be written. So reg data came from the output of the ALU, which is ALU result, and reg source will come from the RD register, which contains the ID of the destination register. So since reg data is already populated, we can in parallel issue a write in the register file, and the write will happen in one cycle, and then we are done. So we jump to the beginning of the preamble. Alright, so we have done instructions of the form move and not, and also 3 address format ALU instruction. So let's see what's left. The compare instruction. So the compare instruction is also simple. So now that we have gotten a hang of microprograms, my speed of going through these programs will slightly increase. Just in case you are not able to understand me, my advice would be that please go back, 1 slide, 2 slide, 3 slides, and then try to understand that part. Also read the relevant sections in my book, and after that you will be able to understand these things. So they are very simple, but you just need to get a hang of it. So the compare instruction, same thing. Compare instruction, recall that it does not have a destination, it has 2 sources. The first source is always, a compare instruction is always of the form, it has one source in RS1. The second source can either be RS2 or it can be an immediate, right, IMX. So let's first read RS1. So we transfer the contents of RS1 to reg source, right? So the ID of what needs to be read. That is sent to reg source, simultaneously a read command is issued. So in one cycle the result is ready. Result meaning the contents of RS1 from the register file is ready in regval, which is transferred to the first register, a micro register in the ALU, which is A and B. So recall that for the ALU, there are 2 micro registers, A and B, and the ALU computes some operation on the contents of A and B. So for A, we have loaded the first argument, the contents of RS1. Same thing, once again, we check the value of the immediate. If it is 1, we do something. If it's 0, we do something else. So we've always been explaining the one case first. So let's try to stick with the same tradition. If it's an immediate, well, it's very simple. We move the contents of IMX via the shared bus, of course, to B. And since A is already pre-populated right over here, we send the compare command on the bus, right, via the args mechanism. We send the compare command. So the ALU will populate B in parallel, also do the comparison. In one cycle will be done. However, if the second source is a register, no problem. Let's read RS2, and to read it, we save RS2 in reg source and also issue the read command. In one cycle, the result is in regval, which is sent to B, right? B again. So B can either get its value from the immediate, from IMX, or from the register file, doesn't matter. And we simultaneously issue the compare command to the ALU. And so we are ready with, so mind you, when we are doing a comparison, the ALU result will contain nothing. What will happen is that the results of the comparison will populate the flags register. So we can read flags.e and flags.gt at a later point of time to figure out what was the result of the comparison. So the compare instruction will not write to any registers. It does not have any register side effect per se. It will just modify the flags. So all right, so now that we have so now basically what we do is in this path, once we have done the comparison, we can actually jump back to the preamble. In the other case, once we have done the comparison, we can also jump back to the preamble and we thus exit. Alright, let's continue our journey. The NOP instruction, well, this cannot be simpler. You'll be really happy to see the code. We do nothing at all. We just jump to the beginning of the preamble and we are all set to load the next simple risk instruction. We just jump to the beginning, mb.begin. Now let's look at the load store instructions, right? The memory instructions. So they are also very easy. Everything is very easy in our setup, right? Nothing is hard at all. You know, if you think it's hard, it's just in the mind. So the load instruction works. I'm sorry, instead of ID, this should be L. So let me just note down the slide number such that I can fix it. So the load instruction works like this, that the format of the load instruction is that we actually write to a destination register and we have an immediate which contains the offset and RS1 contains the RS1 is the base register. So this is the format of the load instruction. So what we do is we read RS1 first. So we read it by transferring the contents of RS1 to read source and by transferring the read command on the bus. So then the output of the register file will have the contents of some register whose ID was in RS1. This is regval. So what we do is we transfer this to the ALU and so basically the ALU which has two operands A and B. One of the operands is the contents of RS1. Subsequently, what we do is we calculate the effective address, which is basically the contents of the RS1 register plus MX, right? Well, not the RS1 register, but essentially the RS1 contains an ID of a register, so the contents of that register plus MX. So what we do is we move MX to B. So pretty much we move MX to B. And in parallel, we issue an ALU add operation to compute the memory address. So we're adding A, which is the base address, and B, which is the memory offset. So we're adding both of them via the ALU. So the result of the addition will be saved in the micro register ALU result, right? So what we will now do is that using the shared bus, we will transfer the address ALU result to the memory unit. So recall that in the memory unit, so maybe let me just erase and redraw. Let me erase all of it. So recall that in the memory unit, we have the data memory. We have the MAR for the memory address register and the MDR, which is the memory data micro register, but MDR in this case is not required. So what we actually do is via the shared bus, let me call it SB, we transfer the ALU result which contains the address of the memory location. This we transfer to the MAR register and in parallel we initiate a memory load. So we send the load command. Alright. So we send the load command and we write to the MAR register and also this data is sent to the data memory and in parallel we send the load command as well. So in one cycle we expect that the data memory is accessed and the result of the load is available in the output register of this micro register of this particular stage, which is the LD result micro register. So LD result contains the output of the load. Well, so what's left? What is left is that we need to write the contents of LD result to the register file. How will we do that? Well, that's very easy. We have done it many times now. We transfer the contents using an mmove instruction. We transfer the contents to the reg data microregister, right? Because this contains the data that needs to be written. In subsequently, in the next micro instruction, we read the ID of the destination register RD, right? So we read its ID and we transfer that to reg source because reg source is supposed to contain the ID of the register. And in parallel, we issue the write command. So the write command will essentially write the load result to the destination register, right, in the register file. So since we have discussed this mechanism a few times before, I'm not going into the details, but pretty much to summarize the load operation, we first read the contents of the base register, write it to the ALU. We read the immediate, which is the memory offset. We write that again to another ALU register and also simultaneously initiate an addition. The addition's result is the memory address. This is sent to the memory unit, and in parallel we initiate a memory load. After that, what we do is once the load result is available, we write it to the register file, and the ID of the register that we'll write it to comes from the RD field. So once the load is done, we can jump back to the beginning of the preamble by doing an unconditional jump to the .begin label. Well, we did load, so symmetry says that we have to do store. Alright, so store has the same format technically, but recall that in a store a little bit of an exception was made in a sense that store does not have a destination, it rather has two sources, and that's fine. One of them is the address source and the other is the data source. So this is also a register which contains the data that needs to be stored in the memory address. So we have discussed the store exception. So let me say how this is implemented in microcode. So what we do is that we do the same, two lines are common. We transfer the contents of RS1 to reg source and we initiate a register read. And the contents of the base register go to the ALU register A. We subsequently read the value of the IMEX. IMEX is the offset, the immediate. This is sent to the ALU via its microregister B. We then initiate an add operation in parallel. So the ALU result contains the memory address. And the memory address is then sent to the MAR register on the memory address register. So recall that the memory access stage with the data memory, DM for data memory, is organized like this, that we have an MAR and MDR micro registers and of course some arguments that come from the shared bus, SP for shared bus. So in the MAR register we save the result of the ALU operation which gives us the memory address, and for the reg source, so reg source is the ID of the register that we either need to read to or write to. So what we do is we populate this. So how do we populate it? So what we do is that we read the ID of the RD register. So in this case, the RD does not contain the destination, rather it contains the data that needs to be stored. So in any case, we need to read it. So we read it by transferring its contents to reg source and initiating the read command. After that, the value is there in reg val. So this is transferred to the memory data register MDR. So basically the value comes to the MDR register, right? MDR. So this is the value that needs to be stored in the data memory. So in parallel, in the previous case we had a load command that we are issuing. In this case we issue a store command, store to the data memory DM. All right. So this is this what will it do? Since the memory address has been pre-populated in this line, so let me maybe do a little bit of erasing. since the memory address has already been populated in advance by the contents of an ALU operation, now what we are doing is we are reading the next operand, which is RD, reading its contents from the register file and transferring it to the memory data register, which contains the data that needs to be written to the data memory in a store operation. And since the rest of the arguments are all there, we can in parallel initiate a store operation via the args field, and that will store the data to the data memory. Well, then we are done. So we just have to then, migrate back, jump back to the beginning of the preamble for the next simple risk instruction.